So good morning. Today we will prove the Thouless theorem, and hopefully we'll have enough time to start talking about the Hartree-Fock equations, which we will derive here using a combination of the Thouless theorem and diagrammatic methods. So you remember last time we essentially completed our discussion of diagrammatic methods. We discussed the usefulness of Goldstone diagrams in the calculations involving spin-independent operators, and then near the end of the last lecture I started talking about the independent particle model approximations that are behind various mean field theories, such as the Hartree-Fock theory, which is of interest to us here. Okay, so let's prove the Thouless theorem. Let me first state it. So let's imagine that we have two slated determinants, phi and phi tilde. And let's assume that these two spin orbitals have a non-zero overlap, meaning that the inner product phi and phi tilde is not zero. Then we'll be able to prove that phi tilde is related to phi as follows. It is proportional up to some constant to the expression where we are exponentiating the one-body operator C1 and then acting with such an operator e to the C1 on phi. So C1 here is a standard one particle, one hole excitation operator. So I'm writing the standard definition of it, okay, where we're using the notation that the I symbols, or throughout the proof, I, J, K symbols will correspond to indices occupied in the phi, and the A or B or C, little a or little b or little c, will be indices that correspond to spin orbitals unoccupied in the phi. So one way you can read this theorem is such that if you have two determinants which have a non-zero overlap, then you can state that there always exists a one-body operator C1 that transforms one of these determinants into another using this formula. Okay, but what we'll do here, we'll actually not prove the Thouless theorem sort of using the existence statement. We'll actually construct the C operator explicitly. We'll actually see what it is. Okay, what is the form of an operator C1 that brings one determinant into another, which is, I guess, more useful, because then you can really do something about it. Specifically, actually, we will focus on the case where determinants phi and phi tilde satisfy the intermediate normalization condition, which I'm writing here. That is, we will assume throughout the proof that the overlap of phi and phi tilde is 1. You can always produce this condition from here. If this is non-zero, then of course all you need to do is to divide phi tilde by the overlap phi and phi tilde, and then you will satisfy this condition. So this condition is always easy to satisfy, and so I'll be making such an assumption. That's a very important condition, as you will see later in Kappa-Caster theory and in perturbation theory, MDPT, and we'll use it also here. So this will be assuming the intermediate normalization condition that states that if you form an inner product of phi and phi tilde, then you get 1. As I said, if this is not satisfied, all you need to do is to divide by phi tilde by a constant, and you end up with this formula. Okay? If you satisfy this condition, then the Thouless theorem is actually this: phi tilde equals e to the C1 acting on the phi. Okay? There's no constant in front. It's simply e to the C1 acting on the phi. Okay? So that's the statement we will prove now. Okay? All right. Let me start by writing definitions. Okay? So we will represent our determinant phi as a determinant obtained, as a straight determinant obtained from spin orbitals 1, 2 through n okay, which belong to a basis set of p's, single particle states p, okay, with all I'm doing here, I'm picking up n members of this basis to construct my determinant phi. Similarly, phi tilde will be a determinant which is spanned by or produced by n members, n spin orbitals from a basis set which I will call p tilde. Okay? I already talked about it last time, but let me remind you, why do I have to do it the way I'm doing it now? Okay? If you have a determinant phi, okay, consisting of spin orbitals 1 through n, you cannot create a determinant phi tilde that is of interest to us by simply picking up another subset of indices from the basis set p, because if you did just that, then you would produce an excited state determinant relative to phi. But excited determinants are orthogonal to the phi, so we would not produce a determinant that would be non-orthogonal or overlapping with the phi. So the only way for us to get the determinant which is actually overlapping with the phi in a non-trivial way is by rotating the basis. We really have to go from one basis of spin orbitals to another basis, okay, and then construct the new determinant from the rotated basis. Okay, so that means that we'll be really interested in relating our new basis of tilde spin orbitals with the original basis of the untilted spin orbitals. And the relationship, of course, is well known to you. It is, I can write it this way, where the d coefficients are nothing else than transformation coefficients from the original basis set of the untilted spin orbitals to the basis set of the tilted spin orbitals. Okay? This is, of course, a unitary transformation because we are transforming one orthonormal set into another. Okay? So you know from algebra that the transformation that is responsible for going from one orthonormal set to another must be a unitary transformation. Okay? We'll not be using this a lot, but obviously this must be true. Of course, you know, what I want to do here, I want to use techniques of second quantization. So let's write our determinants using second quantization. So the first determinant can be obtained by forming a product of xi dagger operators, running where I runs from 1 to n, acting on the true vacuum. Explicitly, it's x1 dagger through xn dagger acting on the true vacuum, where x dagger operators with no additional symbols at them are operators associated with the basis set P. Okay? Well then, I can write a similar expression for phi tilde. It's going to be a product of xi tilde dagger operators acting on the vacuum. Okay? Explicitly, once again, it's a product of x1 dagger tilde times xn dagger tilde acting on the true vacuum. Okay? So now I have my second quantized expressions for phi and phi tilde. Phi in the original basis of p's, phi tilde in the new basis of phi tildes. And in order to establish the relationship between phi tilde and phi, that's what Thouless theorem is all about. You have to find the relationship between the tilde creation operators and the untilted ones. Okay? In our initial considerations. So let's do this. So, you know, in order to do this, I have to just go back to this expression. If you look at this expression, I can write it, maybe I'll do it here, as x dagger p tilde acting on the vacuum, okay? Because when you apply the creation operator p tilde to the vacuum, you end up with this single particle state p tilde. That's the left-hand side. And on the right-hand side, I will have a summation over p of d p tilde p sum over p. And here, instead of p, I can simply write the creation operator xp dagger acting on the true vacuum. Okay? Well, this certainly must be true for every p tilde. Okay? So all I need to do is to find the relationship between the creation operators in the old and new basis sets. All I need to do is to just drop the vacuum. So that is telling us that the creation operator x p tilde in the new basis is simply obtained by transforming the creation operators for the untilted basis, okay, with exactly the same coefficients d that you use to transform the basis. Well, that is sort of obvious, I guess. We would expect this, but it's sort of good to see such a question. Of course, you could write a similar relationship for the annihilation operators. We don't need them, so I'm not going to write it, but you can easily see that all you need to do is to form a complex adjoint of the d coefficients, and then you would have a relationship for the annihilation operators. We are actually not interested in this formula for any p tilde. If you go back to our definitions of phi and phi tilde, I actually want to know what are these creation operators where our index runs from 1 to n. Okay, that's all I really need. So I'll write this equation for p tilde being I, being one of the occupied states. Okay, so then this relationship becomes xi tilde dagger equals a summation over all members of our original basis p d I p x p dagger. Okay, this is our, I would say, initial expression that we need to now start working on. Since I'm really interested in relating phi tilde to phi, and in the phi our x dagger operators are labeled with indices 1 through n, I will split this summation into the part where p runs from 1 to n, okay, and then the rest of it. So in other words, I'll split the summation over all spin orbitals into the occupied part and the unoccupied part. Okay? Well, let's do just this. Let's see, somewhere here. Okay. So what do we get? That xi dagger equals a summation over, say, indices j running from 1 to n, and then we have d I j x j dagger. Okay, so that is sort of the occupied transformation of particle transformation, and then the summation over b that starts with n plus 1. This is the first unoccupied state in the phi, going to, well, where it's going here, it depends on the basis. Okay, I'll put infinity, assuming that we're dealing with infinite basis sets. Okay, but of course, in practice, that infinity would have to be replaced by whatever is the size of your basis in the actual calculation. So then we have d I, say b, x b dagger. Okay. Since I'll be doing more manipulations, I will actually introduce a new notation where coefficients dij will be called fij. Okay, and that is coefficients that are combined, that are responsible for the transformation within the occupied block of spin orbitals will be called f's, and the coefficients that are responsible for the transformation from the occupied to unoccupied spin orbitals, I'll call them g's. Okay, so g I b here. Okay, so let me rewrite it. Let me rewrite this. So we have then xi tilde dagger equals a summation over j from 1 to n fij xj dagger plus a summation over b from n plus 1 to infinity, if we have an infinite to many spin orbitals, in our basis g I b x b dagger. Okay, this is going to be one of the useful expressions for the calculations I'm going to be performing right now. Okay, all right. So far I haven't really said anything extremely new or surprising. I just wrote definitions of the determinants. Okay, in two different basis sets, and I related the old basis to the new basis within the context of second quantization. That is, within the context of creation operators that are responsible for creating the phi and phi tilde. Okay, so you could always write such things. The thing is that we have to now go back to our assumptions. In Thouless theorem, we're making an assumption that the overlap of phi and phi tilde is non-zero. Okay? So we will first examine the consequences of this statement on our coefficients f and g. That is, there must be some constraints on the f's and g's, or maybe on the f's only, all right, resulting from our assumption in Thouless theorem. Okay? So let's examine this aspect. So what I'll do, I'll simply compute the inner product of phi and phi tilde, using definitions that we have. So what is phi? Phi is a product of the creation operators acting on the vacuum, through vacuum. If I want to know the bra phi, I have to, of course, replace x daggers by x's, the ket vacuum by the bra vacuum, and write these operators in a reverse order. So my first part will be simply vacuum here, and then xn going up to x1. Okay, that's the phi. What about phi tilde? Well, phi tilde is just the product of creation operators, x1 dagger through xn dagger, of course, all with the tildes. Okay. Well, now we know how the tilde creation operators are related to the untilted ones. So I'm going to stick this formula into this formula. Okay? It's going to be a little bit of a mess for a moment. It always is, right? But we'll, of course, eventually clean it. So what you can see, what you'll end up with is this. We have vacuum, a product of the annihilation operators, and then we have, for x1 dagger, we'll have a summation over, say, let's call it j1, running from 1 to n, f1 j1 x j1 dagger, plus a summation over b1 from n plus 1 to infinity, g1 b1 x b1 dagger. Okay? This is simply the explicit form of x1 dagger. Okay? As you can see, I'm following this definition, and I'm replacing j here by j1 because I'm going to have many of these j's now for each of the creation operators. Okay, so I have to find some sort of a notation for it. Let me actually, to be more clear about it, let me write maybe the second term, and then I'll write the last term in our product. Okay, so the second term, that means the term corresponding to x2 dagger, will be a summation over j2 running from 1 to n, f2 j2 x j2 dagger, plus a summation over b2 running from n plus 1 to infinity, g2 b2 x b2 dagger. This is not simple, x2 x2 dagger tilde. Okay, and then the last term, if I continue after some dots, will be a summation over jn running from 1 to n, fn jn x jn dagger. So that's the f part. Okay, and then we'll have the g part, which is a summation over bn running from n plus 1 to infinity, g n b n x b n dagger. Okay, so this is an explicit formula for xn tilde dagger. Okay, written down here. And then we have the vacuum to close our expression. So as you can see, what I have here is a bunch of annihilation operators first, and then I have these bracket expressions, each of them having two components, the f component and the g component. What I'll do, I'll simply split it, okay, and start working out the formula that I'm interested in. So what is the overlap of phi and phi tilde then? The leading term will be a term obtained by picking up the f pieces from each of the bracket expressions. Okay? Is everything okay? Alright. So what we have is the summation over j1, j2 through jn, running from 1 to n. Okay? You will have f1, j1, f2, j2, fn, jn. Okay? And then we'll have 0, xn through x1, and then we'll have xj1 dagger, xj2 dagger through xjn dagger, and I will have to close it with the vacuum. That's the leading term that I obtained by simply picking up all the f pieces, okay, from each of the bracket expressions. Well, then there will be other pieces, of course, obtained by picking up one or more g components of our bracket expression. So let me actually write one of them so that we have something like a basis for our discussion. Okay, so the next term would be a summation over b, say 1, okay, a summation over j2 through jn, from 1 to n. Here b1 goes from n plus 1 to infinity, okay? And that term will be a term where I pick up the g piece from the first bracket expression, and I pick up the f pieces, f2, j2 through fn, jn, from the remaining bracket expressions, and then I have to deal with an expectation value of, in the true vacuum, of xn through x1. Then you will have, from the first term I picked up the g, so that's xb1 dagger. From all the remaining ones I picked up the x daggers with the occupied symbols j2 through jn, and I have to close it with the vacuum, okay? Well, you can imagine the next term will be the term where you pick up the g from the second bracket, you know, and so on. Of course, then you'll start picking up pairs of the g terms, right, from each bracket. And then, you know, if you continue doing this, the very last term, okay, that's what I'll write now, will be a term where you pick up the g components from each of the bracket expressions. Okay, so let's actually have it also for completeness. So we have a summation over b1, b2 through bn, running from n plus 1 to infinity. Now we have g1, b1, g2, b2 through gn, bn, and then we have an expectation value in the true vacuum of xn through x1, xb1 dagger, xb2 dagger through xbn dagger, and closing with the 0. Okay? That's what we get. Well, let's analyze all these terms. Let's start actually with this one. Okay? You can see that now we are computing expectation values in the true vacuum. But you know from our rules developed a long time ago that when you have an expectation value in the true vacuum, you have to consider fully contracted terms. Okay? We are talking about the true vacuum, so those will be fully contracted terms with contractions from the bottom, written from the bottom, not relative to the true vacuum. Well, if I start fully contracting this, okay, I cannot contract these operators among themselves because x contractions are 0. So I have to take one of these x's, or each of these x's, and contract with x daggers. Certainly, among these contractions, there will be a contraction of one of the x's with this one. Okay? What is this contraction? This is a contraction of the xi, xb dagger type. X with an occupied index and xb. Okay? This type of a contraction. And if you really think about all the remaining terms, there will be at least one contraction of this type there. One of the x's with one of the xb daggers. If you have more, of course, there will be more of them. Okay? But if you go back to our, essentially beginning of our course, when we introduced actually the contractions for the first time, you remember this is actually delta IB. But I is occupied, B is unoccupied, so that delta can never be non-zero. Okay? So you end up with a 0, meaning that all these contributions that contain the G terms vanish. Okay? Because there's at least one contraction in them that produces a 0. Is this clear to everybody? Everybody? Just to give me some sort of a signal, right? If need be, I can say it again. Is it fine? Okay, good. So, alright, so what I'm going to do now, of course, I'm going to do the following. I'm going to say that all that work was for nothing because this is 0. Alright? All these terms, including the last one, are zeros. Okay? That means that we're only left with the first term. But if you look at the first term, we can also simplify it further. Okay? So let me now go to this blackboard to do this. You can see several things about this term. First of all, so maybe I'll start writing, but not yet the complete expression. So what I have there is a summation over the J symbols. Let's look at these J symbols. They're running from 1 to n. Okay? In principle, in the summation, they are not constrained. But actually they are constrained. Because if two of these J's are identical, you end up with a square of x dagger, but square of x dagger is 0. Okay? In other words, you can make an assumption that these j's are different. Okay? Because the ones that, you know, the ones that where we have where some of them are the same, all those situations will produce a zero result. So we end up with, okay, let me make sure this is properly cleaned. Okay, we end up with a summation over J1 different than J2, different than, say, Jn, all running from 1 to n, and then we have F1 J1, F2 J2, Fn Jn, and then we have an expectation value of xn through x1, xj1 dagger, xj2 dagger, xjn dagger 0, okay? But now let's think about it some more. Okay? First of all, if all these indices run from 1 to n, and they are all distinct or different, that means that they must be permutations of integers 1 through n. Okay? So each of these set, j1 through jn, is a permutation of 1 through n. Let's call this permutation p. Okay? It's a permutation that replaces 1 through n by j1, j2 through jn. Okay? Well, that means that what I really have here is a summation of permutations of indices 1 through n. Okay? So let me keep writing. I have here a summation of permutations of indices as, we use the symbol Sn for the group of permutations of n symbols. Okay? And then the question is, what else do I have? Well, you remember, we are talking about the expectation here, expectation value here in the true vacuum. So I have to perform a full contraction. So x1 must be going somewhere where x1 dagger is in this permutation. x2 must be going somewhere where x2 dagger is. xn must find its partner here. Okay? And so, so do those, right? So there will be, all possible contractions involving x operators with their x dagger partners. Okay? Of course, typically scrambled because the j's are permuted. Okay? So that, but let's make a note. We're talking about the fully contracted terms. Well, if I unscramble these contractions, that is, rearrange operators such that x1 runs into x1 dagger, x2 runs into x2 dagger, and so on, okay, I will have to introduce the sign of the permutation, this permutation here, okay, and then we'll have f1 j1, f2 j2 through fn jn, and then I'll have a very nice expression xn through x1, x1 dagger through xn dagger, okay, where you contract 1 with 1 dagger, 2 with 2 dagger, n with n dagger. Okay? But of course this expression is 1. Because each of these contractions is 1. So you have a product of 1s, okay, done n times. So, I can say that this is, there's favorite color. Alright? So this is of course 1. So all I'm left with really is this part. Okay? But if you really look at it, because given the fact that j's are permutations of the original symbols 1 through n, then this is nothing else than a definition of the determinant of matrix F. Okay? So we end up with a determinant of a matrix of coefficients Fij, where ij runs from 1 to n, which I will call this matrix F, and I will underline it with, wavy line. Because wavy line, when you print this stuff, is regarded by printers as a bold symbol. Okay? So I'll stick with the old convention. And when you have to do this in your manuscript, when you have to type them, I remember times on typewriters, you have to type things, and then you have to tell your publisher what is bold. And you communicate to them by putting a wavy line, unless your typewriter was so fancy that it could produce the bold symbol. Right? I don't know. Do you have those? I don't remember. Anyway, I never had one. Okay, but here is student, you can therefore the fanciest typewriters right there.
You had to mark it in red.
You had to mark it in red, okay. Yeah, but I remember the way you like that there was a double line, was I think Roman, single underlining was italics, So you had a way to communicate to people without having PDF files. Okay. Anyway, going back to where we are, okay, if you look at this consideration, we are assuming that this is not 0, meaning that this matrix, the determinant of this matrix of coefficients must be not zero. That means that this matrix F must be non-singular. Okay? Well, if it's non-singular, we can invert it, and we'll use this information in a moment. But actually, specifically, in our proof, as I said, we'll be assuming that the overlap of phi and phi tilde is 1. Well, what is the consequence of it? The consequence of it is that the determinant of matrix F, which corresponds to this occupied to occupied transformation of the untilted to tilted spin orbitals, must be 1. Okay? So let's remember this fact, because we'll return to it in a moment. So, okay. The next thing is, okay, so I know now phi, I know phi tilde, we still got them here, okay? We know how to transform from x's to x daggers to the tilted quantities, and we know that the coefficients f have a constraint, okay? If you want to retain the intermediate normalization, the determinant of this little matrix, square matrix n by n matrix f must be 1, okay? And I could, of course, start computing using all this information, but I will do one more thing. I will try to replace phi tilde by a sort of nicer form of it, okay? By performing one additional transformation. So this is still, we're still sort of in this preparatory steps, right? I'm not proving Thouless theorem just yet, I'm preparing the way. Okay, I'm trying to make sure that quantities we're operating on are as simple as possible. So what I'm going to do now is I will transform our tilde occupied spin orbitals into the double tilted form, okay, in the following way. It's f to the minus 1, I, j tilde summed over j from 1 to n, okay? So as you can see what I'm doing, I'm transforming our tilted spin orbitals that are occupied in the phi tilde using f to the minus 1 transformation. Okay? Now let me explain why do I want to do this. First of all, the question should be, can I do this? Well, yes, I can. We just proved that matrix F is non-singular, so that means that f to the minus 1 exists. So I certainly can write this expression. That's a legitimate expression. Okay? Second thing is that if you transform spin orbitals in a determinant, and our determinant of f is 1, so that's a unitary transformation really. So if you transform your determinant, rows or columns in a determinant by a unitary transformation, you don't change the determinant. So we expect that by doing this trick, okay, I'm not going to change our determinant. That is, the new determinant, let's write it as phi double tilde, which will be written from these double tilted spin orbitals, which will be constructed from these double tilted spin orbitals. We expect it to be the same as phi tilde, okay? I haven't proved it yet, so I'll put the question mark, but certainly from your knowledge of algebra, you should expect that result, because we are transforming, you know, our spin orbitals, which form, say, rows in a slated determinant. We're transforming them with some unitary transformation, and that, of course, cannot change the determinant, okay? So we expect this result, but let's prove it. In order to prove it, of course, we're going to be using again techniques of second quantization. So what is phi double tilde? Phi double tilde is the product of creation operators x double tilde x1 double tilde dagger through xn double tilde dagger acting on the vacuum, where these creation operators with two tildes are related to the tilted creation operators the same way, you know the spin orbitals here are related. So in other words, we can say that x double tilde I dagger is a summation over j from 1 to n, f to the minus 1, I j x j dagger tilde. Okay? So, you know, I hope it's obvious, right? Because if you apply this equation, both sides of it, to the true vacuum, you will end up with the transformation of spin orbitals. Okay? So, what I will do now is I will try to use this equation, which tells us how the tilted creation operators get transformed into double tilted ones. Okay, I'll try to use it to prove that phi double tilde is phi tilde. Okay, let's continue then. So what do we have? from each double tilde creation operator, we end up with a summation over j. So I'll end up with a multiple summations over j1, say, through jn, all running from 1 to n. We have f to the minus 1, 1 j1, through f to the minus 1, n jn. Okay? And then we'll have a product of x j1 tilde dagger through x jn tilde dagger, all acting on the true vacuum. Okay, so all I did right now is I replace each of these x dagger operators with two tildes by this formula. So we end up with summation over j1 through jn, dots here. Okay, and then we have the product of this f to the minus 1 matrix elements, okay, and then we have the product of tilde x dagger operators. Well, you can see that once again we have these j indices all running from 1 to n, okay, and in principle we are having them unconstrained here because that's how we obtain this equation. However, they cannot be the same. Okay, if two of these indices are identical, then you end up with a square of x dagger, square of x dagger is 0, and you end up with a 0. Okay, so I can set to make an assumption, and I'll do it perhaps on the different blackboard, that these j indices in our summation are all different. Okay? So that means that if I continue here, phi double tilde is a summation over j1 different than j2 and so on, different than jn, all running from 1 to n, and then we have f to the minus 1, 1 j1, f to the minus 1, n jn, and then we have x j1 dagger tilde through x jn dagger tilde acting on the vacuum. Okay? Well, if j's are running from 1 to n and they're all different, that means that they must represent the permutation of indices 1 through n. So once again, we have a permutation here that transforms indices 1 through n into j1 through jn. Okay? So if I now realize this fact, this is simply a product of the x1 dagger through xn dagger with tildes, okay, times the sign of the permutation, because all I need to do is to repermute. So I end up with the formula that phi double tilde, as you can see, is a summation over permutations now, because all these j's are here, permutation, some permutation of 1 through n, okay, and then we end up with sign of the permutation, f to the minus 1, 1 j1, meaning 1 permutation of 1 into j1, okay, then f to the minus 1, n, jn, and then you have x1 dagger tilde through xn dagger tilde acting on the vacuum, okay? Well, you recognize that this part here, that's phi tilde, right? Well, and what is left is this part. Well, what is this part? That's a determinant of matrix f to the minus 1. Simply, right? That's the definition of it, really. So, with all of this, I can state right away that phi double tilde is phi double tilde is a determinant of matrix f to the minus 1 times phi tilde. Okay, so we already can see that phi double tilde is proportional to phi tilde. Okay, but we already know that from the intermediate normalization condition that we are imposing, that is, remember this condition, that phi overlap phi tilde is 1, implies that the determinant of f, we already proved it, is 1. But if the determinant of f is 1, the determinant of the inverse of f is also 1. Okay? So that means that what I am looking here at is 1. Well, that means that phi double tilde is phi tilde, as we expected. Okay? We, surely could have avoided this. I could have just stated the fact, but I think, it's useful to see that second quantization works, even in sort of such algebraic manipulations, right? That are essentially basic algebra of determinants. Okay. But, you can ask a question, why did I do this? Okay, so I showed you that there is a way to transform spin-orbitals in phi tilde so that we don't change it, okay? But the question is, why did I want to do it this way, this or this way? Well, I wanted to do it this way because, as you will see now, the relationship of the double tilted x daggers with the original x daggers is much simpler than the one between the tilted and untilted quantities. You remember the one between untilted and tilted quantities, it involved these f terms and the g terms. Okay? As you will see now, the relationship between the double tilted and untilted quantities does not involve the f terms at all, directly. Okay? It involves them indirectly, but not directly. So let's talk about this. Let's see. So I guess I'll erase, I guess I can erase this. I'll still hold to this. You have it in your notes. Should I do anything? Okay, let me actually do this processing here. So let me now compute xi dagger double tilde. Okay? So we have a formula here. It's a summation over j from 1 to n f to the minus 1 f to the minus 1 f to the minus 1 I j, and then I have xj dagger tilde. Okay? I don't know if I still have this formula. I probably don't. You remember there was a formula relating x dagger tilde with the x daggers. Okay? So I'm going to use it now. Okay? It should be, I'll make sure I don't make a mistake here. Okay? It is a summation over k from 1 to n. Okay? F, j, k, x, k dagger. So that's the f part. Okay? And then there is a summation over, let's call it a b, from n plus 1 to infinity, of g, j, it's j because I'm talking about the xj dagger here, alright, b, x, b dagger, alright? That's what we have. So what I did here, what you see here in the square brackets is simply xj tilde dagger. Well, you can see I can split this expression into two parts. The summation over jk and the summation over j and b. Okay? Well, let's do this. So we end up with the first summation. I'll write the summation over k first, and then I'll write the summation over j. And you will see in a moment why I want to have it in this order. Then I have f to the minus 1 ij times f j k. You sum this over j. Okay? And then you multiply the result by xk dagger. And you sum over k. That's the first contribution. The second contribution will have a summation over b. I'll write this one first. Then a summation over j from 1 to n. And we have f to the minus 1 I, j, g, j, b. Okay, you sum this over j's. Maybe I'll underline. Okay? And then you multiply the result by x, b dagger, and then you sum over b. Okay? That's what we end up with. Alright, well, let's think about this expression now, carefully. So I'll start right here. xi dagger double tilde equals. If you look carefully at the first summation, you are multiplying f to the minus 1 by f and taking up the I, k matrix element of this matrix product. You can clearly see we're having a multiplication of the rows of f to the minus 1 with columns of the f. You are summing over, the summation over j is row by is a multiplication of rows by columns. So the first term has the following form. It's a summation over k from 1 to n. Then we have a product of matrices f to the minus 1 and f, and we're computing the the ik matrix element of it. Ik summed over j. Okay, and then you have to multiply by xk dagger. Okay, let's look at the second term from the same point of view. Alright, well, the second term is a summation over b from n plus 1 to infinity, and then once again you recognize that we have a matrix product here. Okay, we're multiplying matrix n to the minus 1 by, which is a square matrix, by a rectangular matrix G. Okay, so what we have here is on the chalk. We have there f to the minus 1 times G, okay, and the matrix element that we're talking about is IB, okay, IB, you see the I and the B, okay, and you multiply by XB dagger, okay. Now, if you look at this, what is this matrix, just to maybe sketch it, I think people like seeing such things. We have f to the minus 1, which is an n by n matrix, and you're multiplying this by this rectangular matrix which has this shape. Okay, it goes this way. Okay, it's n by the number of virtual or unoccupied spinors in the basis set. So in our case it's infinity, right? If we have infinitely many, but of course it could be finite if we were operating in a finite basis set. So you end up with n to the minus g. It's a matrix which is n by that dimension. Okay, that's what it is. All right. Okay. Well, let's then analyze these terms. What is this one? What is this? 1. This is the unit matrix, right? And what is then this expression?
Delta.
Exactly. It's delta ik because the unit matrix, okay, has ones on the diagonal and zeros everywhere else. So if you keep writing, the first, we end up here with a summation over delta ik times ak dagger, the sum over k. That means that all terms other than k equal I will drop out, and you end up with xi dagger. As I said, that's all that is left. No f matrix elements there. And then for the second one, well, I'm going to call these matrix elements CIB. Okay? So what we have there is a summation over B, CIB, XB, dagger. Okay? Those are the matrix elements of this product of f to the minus 1 and G. So this is a very important formula. So what I'll do now, I'll probably copy it here. Okay? Because we will be using it. And then we'll continue. So let me copy it and then comment on it. All right. So we just proved that by performing the secondary transformation of spin-orbitals tilde into the double tilde form, which doesn't change the determinant phi tilde, it just rotates spin-orbitals in it, we are able to show that xi dagger double tilde, that is the creation operators for the double tilde spin-orbitals, equals xi dagger plus, I'm going to replace b by a now, okay, because I don't need to use b there, plus the summation of unoccupied spin-orbitals in the phi, CIA, that sounds nice, xa dagger. Alright? Where CIA, we have a formula for it. It's not like it's an unknown quantity. We know that CIA is a matrix element of f to the minus 1 times G. You form this product, and you take a matrix element of IA of this product. Okay? Or explicitly, it's a summation over J, f to the minus 1, I, J, G, J, A. Okay? Sum over J from 1 to N. Okay, alright. Okay. No. Alright. Okay? So you can see that in a way the second transformation has a nice property, that is, it's more like a canonical transformation. What you're really seeing is that the new creation operator is an old one plus a shift. which brings the unoccupied orbitals into the calculation, right? You know, if we didn't have this component, you wouldn't change anything. Your phi delta would be phi. But this is really what's responsible for bringing the for transforming phi into phi tilde or phi double tilde. Okay, you need to bring these unoccupied orbitals somehow to be able to rotate orbitals, spin orbitals. If you don't bring unoccupied states, then of course you're not doing anything. Okay? You're not rotating, determinants. You're just rotating spin orbitals, but you're not rotating them. Okay, so that's the important equation. So now we're ready. Well, I guess we're ready now to do the proof. Okay, we've got all the steps. I guess you need a break? A few minute break? Okay, so let's have a 5-minute break till say 9:30, and then we'll complete the proof. I like this theorem. It's not a complicated thing in the end. But it's a very beautiful thing. Because it has many consequences. When you know such theorems, then of course you can explain invariance of Kaplan-Classical results with respect to rotations of orbitals and things of that sort. But you can go beyond this. Of course, you can construct various symmetry-broken solutions by applying the proper definition of the C of this one-body excitation operator. One can produce various symmetry-broken determinants. Of course, the simplest one being unrestricted hard to fog, but you can go beyond this. Various charge density waves, all these things that people study where you break more and more symmetries, right? You can start breaking the S square symmetry, that's UHF. Then you can break SZ symmetry. You can mix alpha and beta spins. It looks crazy that you should not be doing this, but you can. Nothing says in mathematics, nothing says that you can't do it, so you can do it. To break that symmetry, actually, you're producing a determinant which is so symmetry broken that it actually is a multi-configuration state now. It is a state which really, if you translate it back into the hierarchy function orbitals, it will be actually a linear combination of many determinants. So you see, this is a way, the Thouless theorem gives you a way to produce multi-determinantal states that actually are representable by a single determinant with lots of symmetry breaking. It's a fantastic thing. It's very useful for things like strongly correlated systems in physics and so on. Okay? So there's a lot more than meets the eye. Here we needed a very specific context, but I really like the theorem because it brings you so much knowledge without going to complicated 2, 3, and higher level operators. Beautiful thing. You know Thouless, I hope. Do you?
No.
Do you? Okay. He's at Seattle, University of Washington.
Really?
INT. He's in this Institute of Nuclear Theory. He did a lot of things. But he did a lot of things about these symmetry broken solutions and stability conditions and other things like this. Of course, he did a lot more. This is extremely useful for us. Oh yes, I sent this email, right? So I got responses from you. Could you respond to me, Jared?
Yes.
Yeah, okay. Are you okay? Can you tell me? Are you okay with the idea?
Yeah.
Yeah, okay, so please send an email so I have, because by the rules of the university, I need a permission. I don't have it. But I think it's a good solution because it's going to be, we'll have a little bit of review and then, we'll not be so constrained. I mean, that to me is most important. So I don't have to tell you, what, we're leaving this room now. Of course, I set up these problems so you can easily solve them in, say, 1 hour and a half or so. But, some people want to reread and recheck. And sometimes you get trapped in some calculation that's sort of not going your way. You want to sort of do it again. So I think it's good. It's better for me to see that you can actually do it, how you do it, than do some sort of race for time. Okay. So, shall we? All right. Okay, so right now we are ready to prove Thouless theorem. That is, we have the double tilted creation operators that allow us to form the determinant phi tilde through this secondary transformation that we just discussed. Okay, and we know that phi double tilde is the product of x1 dagger double tilde through xn dagger double tilde acting on the on the true vacuum. Okay, so we end up with the following terms. Actually, okay, that's not important maybe, but okay, let's just emphasize 2 of them first. Then, okay. All right. So I'm going to replace each of these creation operators here by the formula in the box. Okay, so we end up with x1 dagger plus the summation over, say, let's call this index a1, c1 a1 x a1 dagger. Okay, that's a substitute for x1 dagger double tilde. All right. Then we'll have, for the second one, we'll have x2 dagger plus a summation over, say, a2, those are unoccupied states, a2, c2 a2 x a2 dagger. Okay? And then, of course, we continue. So the last term will be xn dagger plus a summation over an meaning again the corresponding unoccupied states, cn an x an dagger. And all of this has to act on the true vacuum. As you can imagine, my purpose has to be, I have to somehow, I have a true vacuum. I'm not interested in true vacuum. I want to extract phi. So we have to do various manipulations now to somehow see that somewhere in this stuff, phi, there's a phi. We don't see it yet, but we have to find it there. That's going to be really the purpose. Okay? Well, the first thing I'm going to do is this. I'm going to insert right here, where I'm indicating, the product of x1, x1 dagger, x2, x2 dagger, up to xn, xn dagger. These sort of pairs. I can do this without changing this expression. So let's understand why. Okay, why is it that I can simply take this, write it here, and without then making any changes? Because if you look at the, you can see I have these pairs. x1, x1 dagger, x2, x2 dagger, xn, xn dagger, right? Let's look at one of these pairs. What happens when you apply such a pair, xi, xi dagger, to true vacuum? Using anti-commutation rules, this gives you 1 minus xi dagger xi acting on the true vacuum. Okay, so you end up with a true vacuum and then 0, because xi acting on the vacuum gives you 0. So you see, I can simply insert these operators here without making any changes. You may say, well, why am I making so complicated this now? Well, I have to, okay? To be able to extract the phi, I have to do this, okay? So I don't have some fancier answer than just this, okay? That's the way the proof goes. All right, so continuing, phi tilde or phi double tilde is x1 dagger plus a summation over a1 c1 a1 x a1 dagger, x2 dagger plus a summation over a2 c2 a2 x a2 dagger, and then times xn dagger plus a summation over an cn an x an dagger. So I just repeated what I had there, I hope correctly. All right, and then we have x1 dagger, x2 dagger, and then xn dagger acting on the true vacuum. Now before I fall on the floor, fix my shoe. Sorry about that. Okay. So now we're going to do the following. You can take x1 dagger and you can move it right here. Okay? Why? Because x1 dagger commutes with everything in front of the first bracket expression. You can easily see it. Suppose I want to move this to the next location. See, you have x1 commuting, anti-commuting with xn dagger, but you also have x1 dagger, also anti-commuting. If you are moving two operators, each of them is anti-commuting, then you're not going to change the sign. So it really commutes. If you look at this is occupied, this is unoccupied. So this pair, again, commutes with xa dagger. So you can move it somewhere here. And in the same way, you can keep moving it up to, and end up here. Of course, you cannot move it any further, if you wanted to try, because there is x1 dagger that prevents you from doing this. Okay, so you have to stop at the location where there is x1 dagger. In the same way, I can take this, let's use some other color. Okay, I can take this pair and move it in front of this, right? Once again, I can definitely move it here because that's n, that's 2, right? And I can keep moving it until I hit the place where there's x2 dagger, right? And we can keep moving these operators in the appropriate locations, so you end up with the following. If I move x1 dagger here, it will multiply both terms. So you will end up with x1 dagger, x1 dagger, the triple of product, then plus a summation over a1, c1, a1, x a1 dagger, x1 dagger. Okay, that's how the first bracket expression will look like after this manipulation. Okay, then the second term, when you move x2 dagger in front of it, it will be x2 dagger that you had, x2 dagger that you are inserting into it, plus a summation over a2, c2, a2, x a2 dagger that we had, times x2 dagger that I am now inserting. Okay? That's how the second bracket expression will look like. And then of course, you can write the third and the fourth and so on, as many as you have. The final one will be what you see here. This times this. Okay? In other words, you will end up with xn dagger, xn dagger, the triple product here, plus a summation over an, cn, an, xan dagger, xn dagger, close the bracket and act on the vacuum. That's what this expression is now. Okay? Alright, well it looks like it's very complicated now, so I made it even more complicated, right? But that's about as as I can do, right? In terms of making it still more complicated. Now I'm going to start simplifying things. The first observation that we can make here is that we have these triple products here. x1 dagger, x1 dagger, x2 dagger, x2 dagger, and so on. xn dagger, xn dagger. Let's actually analyze these triple products. Alright? So what we have there is that xi dagger, xi dagger, right? With the same I at each operator. Well, let's use the rules of second quantization one more time, the anti-commutation rules. We end up with xi dagger times 1 minus xi dagger xi. Well, that becomes xi dagger minus xi dagger square xi. But square of a creation operator is 0. It's a nilpotent operator because of our Fermion algebra, right? So this is 0. So we end up with xi dagger. So as you can see, I can replace each of these triple products, this one, and that one, by a single operator. So you may say, well, so what's the point? Why did I introduce two operators to learn that you can now get rid of two of them, right? No. See, that's true. I can get rid of them here, but not here. But here, I already begin to see the beginning of Thouless theorem. That's a single excitation operator, okay? So I did it on purpose to build somehow the single excitation operators into the calculations. So, it looks like a lot of work for little, but actually there is a big benefit. I am beginning to see the emergence of the single excitation operators. Okay, so let's continue then. So we have T tilde equals P double tilde equals. I'm going to replace each of these triple products by a single operator. Okay, using this equation. So we have x1 dagger plus a summation over a1, c1, a1, xa1 dagger, x1, x1 dagger. Okay, that's how the first expression will look like. Right? Then for the second one, we have x2 dagger plus a summation over a2, c2, a2, xa2 dagger, x2, x2 dagger. And then for the last one, we have xn dagger. So I replace the triple product by a single operator, plus sum over an, cn, an, xan dagger, xn, xn dagger. Okay? All this acting on the vacuum. Alright? And now the key step. You can see that I have x1 dagger operator here, and I have it here. So I can take it outside the brackets. Okay? I have x2 dagger operator here, and I have it also here. I can take it outside the brackets. Alright? And in the last term, I have xn dagger operator here and xn dagger operator here. So I can also take it outside the brackets. Okay? So that's what I'm going to do. So we end up with 1 plus a sum over a1, c1, a1, xa1 dagger, x1 times x1 dagger. Okay, that's how the first expression will look like. Times 1 plus a summation over a2. Okay, then we have c2, a2, xa2 dagger, x2 times x2 dagger. And then the last term will be 1 plus a summation over an, cn, an, okay, xan dagger, xn, and then times xn dagger. Okay, so you can see that we have these bracket expressions where we have 1 plus some excitation operator, and then we have x1 dagger here, x2 dagger here, and xn dagger there. Okay? You see, I can now move these x dagger operators that I extracted in front of the true vacuum. Why? Well, imagine there is xn minus 1 dagger here. Set I can move it, through the unit operator, and I can also move it through those two, because xn minus 1 will anti-commute with this and anti-commute with that. So it commutes with both. Right? So I can move it here. Right? So you will have now xn minus 1 dagger here. Then I can keep moving all of them. Right? For example, x2 dagger, you can move it across all of these because you always end up either with commuting with a unit operator or commuting with the pair. Okay? So based on this, I can move all these operators in front. Okay? of the true vacuum. So in this way, we have now the following. We have 1 plus a summation over A1, C1, A1, okay, X, A1, dagger, X1. Then I have 1 plus a summation over A2, C2, A2, X, A2, dagger, X2. And then finally, we have 1 plus a sum over AN, CN, AN, XAN, dagger, XN. And I have now all these operators X dagger, okay, that we extracted in front of the true vacuum. Okay? Is this clear to everybody? This is a key step. Because that's the step that allows me to extract the phi. Okay? As you can see, we managed, once again, when we were here, we recognized the common terms, we took them outside the brackets, you know, so I have it, maybe I'll put it in circles now, here, here, and here, and then we moved all of them here, because they commute with what's ahead of them. Okay? And in this way, we ended up with an expression that looks like this, where we have the product of these bracket expressions containing excitation operators and the product of X dagger operators acting in the vacuum, but that's the phi. Okay? So by doing all of this, for the first time we see the emergence of the phi. Okay? So we have now some operator in front acting on the phi. Well, that's exactly what we wanted, right? The question is this operator an exponential? Okay? So, in order to see that this is an exponential, let me introduce some additional notation. Okay, maybe I'll also store this notation here, because it's going to be useful for a few final steps. So first of all, as you can see, in each of these bracket expressions I have X dagger, X pair, occupied and occupied. Well, that's an excitation operator. Okay, so let me remind you the definitions. So when I write EIA, I mean, of course, XA dagger, XI. But we are doing more here. We are, as you can see, we are taking an elementary excitation operator, we multiply it by some constant, and we sum over unoccupied states. So let's introduce the corresponding quantity. I'll call it EI with a tilde. It is a summation of the following type: CIA, XA dagger, XI. Okay? I am summing over unoccupied states, but I'm not summing over I. So you can call it, it is a one-body operator, but with a fixed I. Because you have a fixed I in each of these bracket terms. Here I is 1. Here I is 2. Here I is n. So because they are fixed, I want to define the corresponding quantities. Okay? So you can also write it as a summation over A, CIA, EIA. Okay? Where EIA is the elementary excitation operator, from I to A. Okay. Well, with all of this, let me now write what is phi tilde or phi double tilde. Well, the first term is 1, or the unit operator, to be strict, plus, this is E1 tilde. Okay? So I have E1 tilde, using our definition. The next term is 1 plus E2 tilde. And the last term, when I continue, is 1 plus En tilde. It is n. You see the n here? That's your I equal n, and you're summing over x. Okay? And all of this acts on phi. Oh, this is a nice expression. You see, this is becoming better and better, right? So we end up with a product, maybe I'll write it also in this neat way, 1 plus EI tilde phi, when we multiply over I from 1 to n. Well, you know, when you see a product like this, you can expand it by simply producing various terms that are in it. The leading term, what is the leading term? 1. 1 times 1 times 1 times 1 is E1, right? Of the unit operator. Then you will have terms where you pick up one E and then pick up the unit operators from the rest of the expressions, right? So that's going to be a summation over ei tilde over I from 1 to n, okay? Well, then you pick up two e's, okay? You pick up e's from two bracket expressions, and then the unit operators from the rest of them. So that's going to produce a summation over of products ei1, ei2 tilde summed over all pairs of indices I1 and I2. Of course, all running from 1 to n. I hope that's clear. All right? And then, there will be terms where you pick up E from 3 bracket expressions, and then 4. And then you continue, and you end up with a cluster expansion. Okay? The last term will be the term where you pick up E's from each bracket expression. So just a simple product of E1 tilde, E2 tilde, through En tilde. Okay? All of this acting on the phi. Okay? Well, if this is a sort of a cluster-like expansion, then of course we can now do tricks that you normally do in cluster expansions. Right? That is, I can group these terms according to the number of E operators and then have an expansion that looks like this. Phi tilde or Phi double tilde is the unit operator plus the sum, I'm going to write it like this, sum over R from 1 to n, sum over indices I1 less than IR, running from 1 to n, and then we have a product of R copies of operators E, or I should say EI1 tilde through EIR tilde, okay, acting on the phi. That's what this equation really is. Let's analyze this. When R is 1, you have a unit operator, of course, right? When R is 1, that's a summation, fancy pointer, that's a summation over EIs. That's R equal 1. When you have R equal 2, you will have pairs. That's this one. When R is 3, you have triples of E's, right? And when R is n, then you can only make one choice of ordered indices. That's going to be a straight product, a direct product of these operators, okay? So I have my cluster of manifold expansion worked out. Now, we're going to manipulate it. We have these constraints here, so we're summing over constrained indices I. But I can make them actually unconstrained by injecting the factorial. So you end up with a sum over R from 1 to n, 1 over R factorial, and a summation over this different values, I1 through IR, not just ordered ones, right? So we have I1 here, IR, acting on the phi. Why can I do this? Because, among these, of course, I have I1 less than I2 and so on less than IR, but I can also obtain other ones. The other ones are just permutations, okay, of the original symbols I1 through IR. So in order to go from here to there, I have to prove that operators E commute. If they do commute, then I can write them in any order, and in this way I can produce all these other permutations, and then I have to split 1 over R factorial to eliminate repetitions. Okay? So the key thing here is to prove the commutation. Well, so we have to prove that EI in general and EJ commute. Well, that should be easy for you, because what you end up with is a summation over A and B, CIA, CIB, CJB, okay, a commutator of XA dagger XI for EI and XB dagger XJ. Okay? I hope I don't have to really spend more time on it. You know that this is 0, this commutator, right? Because, this pair commutes with this pair, right? So we know this is 0, so that is a 0. If it's a 0, then I can write these operators in any order, and by simply writing them in various orders, I end up with various permutations, and that's what this represents. But to avoid repetition, I have to stick 1 over R factorial. Okay? But there's more to it. Namely, right now my summation involves different. The indices I cannot be identical, but I can make them identical. Why? Because the square of operator E tilde is 0. So artificially I can build in zeros. Let's prove it. I think I'm following the philosophy of this class that nothing is left unproven. We're going to prove it too. Okay? So I have to know what is E I tilde squared. Okay? Well, from the definition, it is a sum over A, CIA, EIA. You have to square it, so that means you have to write another copy of it. Another copy, you cannot use a summation. That's one of those things we see in the homeworks. You can't use symbol A anymore because A is used here to sum, to make in the first summation. You have to, if you want to sum over sum A, you have to call it differently. I'm going to call it a B. Okay? But I is the same because here we're using the same I. Okay? So it's CIB, EIB. So this really is a summation over summation over AB, CIA, CIB, and the product of EIA, EIB. Well, that product is, well, physically, you're trying to excite a fermion from the same level I twice. So physically, you would say, well, can't do it, because there's only one fermion sitting on I, not two of them, okay? But of course, mathematically, this is XA dagger XI times XB dagger XI. You can just flip these two because they anti-commute. I is occupied, B is not. So you end up with XA dagger, XB dagger with a minus in front. Okay, XI squared, which is a 0 because XI squared is 0. Right? So mathematically you can always do it too. Alright? So that means that it is 0. And if it is 0, when I go back to our calculations here, then I don't need these constraints. So what we can have now is the almost final statement. Maybe I'll still do it a little bit here. That says that phi tilde or phi double tilde, same thing, is one plus a summation over r from 1 to n. Then we have 1 over r factorial. And then we have a summation over I1, comma, IR, okay? EI1 tilde multiplying E up to EIR tilde, acting on the phi. Okay? Can you tell me what this is?
The sum of EI raised to the R.
Exactly. Since each of these summations over i's, I1 through IR are independent, you're really having an R power of the same thing. As Max said, it's a summation over EI. So let's introduce the operator that reflects on it. I'm going to call it C1. Well, you know where this is heading now. It's going to be a summation over I of E I tilde. Okay, what I have here then is C1 to the R's power. Is this clear to everybody? Because these summations are not independent. I made them independent. I worked on it. It cost me the factorial. Okay, we'll deal with it. Okay? So what I have there is a magnificent result now. Namely, we get 1 plus a sum over r from 1 to n, 1 over r factorial, C1 to the r, acting on the phi. Okay? But what is C1 actually? You have to just bring the definition of EI. It's still there. I guess that's our storage blackboard. It's here. So you have to take this partially summed expression and sum it over I now. You have a summation over A here. You're going to now throw another summation over I. So C1 will be a true one-body operator. Okay? This is a summation over I and A of CIA XA dagger XI, or EIA if you like. That is a one-body operator. Okay? And we know how to get the coefficient C. You remember? F minus 1G. That's how we were defining these coefficients C. They were these F to the minus, the product. Matrix elements of the F minus 1 times. Well, this is fantastic, because now you can see this is almost like an exponent, isn't it? In the exponent, e to the x, you write a sum over x to the, I don't know, n over n factorial, n going from 0 to infinity, right? That's exponent. So this is an exponent, except that it is not, because determinate. To get an exponent, you have to go beyond n to infinity. Can I go there? Yes, artificially. Because c1 to the r is 0 when r is greater than n. Physically, that's obvious. You cannot excite a fermion more than n times if you only have n fermions. Okay? You can't do it. So physically, that's obvious. Right? Mathematically, well, obvious too. Right? So what is c1 to the r? It is a summation. It's this thing. You know, I still have it actually, right? Well, let's copy it here. ei1 tilde through eir tilde. And I have to sum over this I1 through IR. Remember, I symbols run from 1 to n. So this is, because we're talking about the occupied states. You can see that if R is greater than n, since these indices run from 1 to n, if R is greater than n, some of these indices have to repeat themselves. Right? Is this clear to everybody? If R is greater than n, since these indices I run from 1 to n, there will be repetitions among them, one or more. But if there is a repetition, we can defer to this rule. You're going to end up with a square of e's, but a square of any e is 0. And they also, I should say two things. They commute, so if the repetition appears such that you have some e's between them, between the repeating ones, right? You can move them to become nearest neighbors, because they commute, and then you square. A square of e is 0. So that means that this is 0, okay, if r is greater than n. Well, if that's the case, well, then we are now achieving the glorious moment, arriving at the glorious moment of this whole derivation. And as we begin to see that phi tilde is phi double tilde is 1 or unit operator plus a sum over r. I'm going to now extend it from n to infinity because I can do it. It's 1 over r factorial c1 to the r acting on the phi. But this is an exponent of c1. And that is a Thouless theorem. Okay? We just proved that phi tilde or phi double tilde, okay, that's fine, is e to the c1 acting on the phi, which is the Thouless theorem. C1 in this calculation emerged as a single excitation operator, okay, with amplitude CIA. It's not an existence proof, it's a nice proof, it's a constructive proof. You could actually get those C's if you are interested to know. In other words, if I give you, let's just go be practical, I give you unrestricted Hartree-Fock determinant, and then restricted Hartree-Fock determinant for the same problem, then I know how to transform spin orbitals from one set to another. That leads to this coefficient, you remember, f and g. And then you simply have to form a matrix product, f to the minus 1 times g. And those are your C coefficients. So you can actually produce those C coefficients in Thouless theorem anytime you know your determinants. But there's an alternative approach. If you don't know your determinants, you know one of them, you have, well, I can generate other determinants. Well, yeah, you know that with various values of the C coefficients, you can produce various determinants. You can actually produce the entire manifold of determinants that overlap with phi. And that's exactly what we'll be doing in Hartree-Fock proof. You know, in Hartree-Fock theory, we are minimizing the expectation value of the Hamiltonian with the single determinant. Okay? In a traditional presentation, you spend a lot of pages to prove what comes out, the Hartree-Fock equations. Here it's going to be different. We'll be simply probing the space of all determinants using Thouless theorem, because Thouless theorem allows me to go around a given determinant, okay, and probe all the determinants that have a non-zero overlap with the one I chose. Okay? So it's sort of a constraint search, you can call it, right? It's a constraint search over all determinants that have a non-zero overlap relative to the one I'm interested in. Okay? So that's how our proof will go. Alright? It's a very useful thing. The idea of constraint search, as you know, has been very important in DFT, for example, proving things there, right? So it's a very important thing to realize that you can do calculations in this way. So we'll be searching over all possible determinants around the optimum one, called Hartree-Fock determinant, using Thouless theorem, and you will see in a few steps the Hartree equations will emerge out of it. As a single diagram. Okay? And then we'll talk a little bit about Bragner orbitals, and then we'll move to MDP. Okay? Alright. So, if you have any questions, please don't hesitate to ask me. Please also respond, those of you who haven't, to my email, if you can. Did you all get my email? Yeah, okay, so please, some of you already responded, so please do so that we can start working on the room. If everybody's in agreement with me. Okay. Alright. So I'll see you on Friday. Thank you very much.